Hi, here we are discussing about your project, a two-stage CMOS amplifier with a high degree of stability for all capacitive loads. Okay, so in this project we designed a two-stage CMOS operational transconductance amplifier or a OTA using 45 nanometers and 22 nanometer CMOS technology. The OTA are very important in many electronic systems such as the sensor interface, biomedical circuit, communication blocks and data converters. They are chosen because they provide a good linearity, adjustable transconductance and low power operations. But when we move to advanced technology nodes, we also faces challenges like reduced intrinsic gain, higher leakage and difficulty in keeping the amplifier to stable at low supply voltage. The main aim of this work is to study how these challenges behave when the same OTA circuit is implemented in 45 nanometer and 22 nanometer. We compare their intrinsic gain, power consumptions and minimal supply voltages required for stable performance. So generally the existing OTA uses a cascading or gain boosting to improve the gain, but this method increases the circuit complexity and power usages. So in this project our goal is to keep the design simple while still achieving a higher gain with a low power voltage. To meet this goal, we carefully optimized the transistor sizing and choosing a suitable biasing conditions and apply an efficient frequent compensations method that keeps the OTA stable across the different loads. The novelty of the work is that we make a natural short channel behavior of 22 nanometer and 45 nanometer device to enhance the gain instead of suppressing it, so which helps in reducing power and without sacrificing performance. So all the simulation modules and waveform analysis and performance measurements are done with using a Tanner EDA tool, and the SEDIT is used for schematic design and T-Spice is used for circuit simulations and WDIT is used for viewing and analyzing the output waveforms. These tools helps as a validate parameters like a DC gain, utility gain, bandwidth and phase margins and power consumptions very accurately. Now we can verify the paper. So this paper is fully designed for the OTA based architectures. Okay, so which means a two-stage OTA based architectures. It will be designed using Miller compensator based OTA architecture. Okay, so here they have given a two design architectures. One is for existing, another one is for the proposed architecture. Okay, so compared to this existing and proposed architectures, they additionally integrated one feedback signal. Okay, so it will be helpful to move the stability. Okay, so this proposed design adds a small replicator, which means that this feedback current that feeds a scaled output stages a signal based into the OTA with virtual ground. Okay, and it's creating a left half pane 0 for stability. This changes advanced such as unconditional stability for any capacitance loads, reduced ringing signals and improved phase margins and no increases in circuit complexity and power consumptions. Okay, so now we can verify the output in the Tanner EDA. Okay, so this is a Tanner EDA design. Okay, so here we have developed two different architectures. One is for existing two-stage OTA and another one is for proposed two-stage OTA. So we have designed two different nanometers. One is for 22 and another one is for 45 nanometer. So this designs it will be done with a 22 nanometer. Okay, we'll verify that. So this is the existing architecture. So here you can analyze the input signals. Okay, so input signals we are given a analog differential signals. Okay, and this is the circuit architecture. Okay, so while running this architectures, we'll get a analog signal input with a differential waveforms and we'll get a DC gain output. Okay, so here you can analyze it. So this is the output and this too is the input. Okay, and here the proposed circuit. Okay, so this is a 2 input. Okay, and this is a output. Okay, and this circuit analysis we have done within a T-Spice. Okay, so here you can analyze the out file, the proposed MOSFET count. So MOSFET we have used only 6, okay, and power consumptions it will become with 1.5 e power minus 4, and the delay it will become with a 3.6117 e power minus 6. Okay, so this measurement it will be updated in the comparisons table. Okay, so here this one is the comparisons for this proposed two-stage OTA. So existing two-stage OTA and proposed two-stage OTA. So it will be covered with 45 nanometer and also for 22 nanometer. So here the 45 nanometer we used for 1.2 voltage and 22 nanometer we used for 1 voltage. Okay, and the capacitance load it will be used for 20 and 100. Okay, and the 22 nanometers it will be used for 10 and 50. Okay, so voltage gain will be get 6 point and 7 point and 4 point and 6 point series. Okay, so in 22 and 45 nanometer as well as proposed and existing, and the input frequency we used 100 kilohertz. Okay, and the input signal voltages it will be used with 0.8 voltages. Okay, which means the amplitude signal is 0.8 voltages. Okay, so offset we given as a 0 volt. Okay, and this comparisons we analyze this in the chart mode, and we have written a abstract document for this project. Okay, title, base paper abstract, improvement of the project, proposed title, proposed abstract, and related notes for this project with the advantages, disadvantages, existing system, proposed systems. Okay, and related notes. Okay, finally come up with the literature survey. Okay, and references. Okay, thank you.
Introducing Nxfee Innovation, your trusted partner in IP design and VLSI research. With over 300 plus completed projects in cutting-edge domains like low-power VLSI design, high-speed data transmission, signal processing, and secure networking, we offer tailored solutions for students and professionals in BE, BTech, ME, MTech, and PhD programs. At Nxfee, you not only get expert-guided projects starting from RIS 6000 Transparency, but also enjoy unmatched benefits like RIS 1000 off on your second project, free documentation, and easy-to-understand video explanations. Plus, our rewarding referral program lets you earn up to RIS 2000 MANTs for every successful referral. Trust us to simplify your research journey with high-quality, affordable, and fully customized VLSI solutions. Visit our website to explore a comprehensive collection of projects, organized year by year from 2014 to 2024. The latest 2024 research projects are now available for publication, along with several 2024 non-completed titles, which are updated monthly with new possibilities. For application-based projects, interface designs, and mini projects, you can also rely on Nxfee for top-quality solutions. We provide exceptional PhD assistance with full publication support and offer an installment payment option, allowing you to pay module by module. Let Nxfee guide you through your research journey with flexibility and expert support. Thank you.